This is section 2.2. Today we're going to talk about inverse matrices. First we're going to define them, and then we're going to talk about how to find them, and then we're going to talk about something called elementary matrices. Let's start with some review from last time. So why don't you pause the video, let me move this over, pause the video, and do number 1 and 2, compute these two products. Okay, so this is a 2 by 3, and this is a 3 by 2, so we're going to end up with a 2 by 2. I always like to know my dimensions before I start. All right, and for the first column, we're going to look at this column of the matrix and dot with the first row and the second row of the first matrix. So we get 1 minus 1 is 0. And then we dot with the second row and we get 2. Now we're going to look at the second column of the second matrix and dot that with the 2 rows of the first matrix. And when you do that, you get 6 up here and then -1 here. All right, and for the next one, UV transpose, U is a 2 by 1. 2 by 1. V transpose, so we're going to take I'm going to turn the columns into rows. So the column 1, 2 becomes the row 1, 2. And this is a 1 by 2. So our product will be a 2 by 2. All right. And we're going to take each, it's funny because each row and each column is just one number. So the first multiplication is going to be -2. And then we get 4 times 1 is 4. And then we get -2 times 1 is the next product is going to be, let's see, -2 times 2, which is -4. And then 4 times 2 is 8. All right. You can read this, go to this link and read this cool application of inverse matrices. It's pretty neat. It's about computer and coding and games, writing games. Let me just show you what an inverse is. In short, an inverse is you have a matrix A and you multiply on the left and the right. If you get the identity, that's called the inverse. So if this is the matrix A here, I'm just going to multiply on the left by this matrix, which I'm claiming is A inverse. We should get the identity. So we get -14 plus 15 is 1. And then I'm going to get -14. So then the second column, so down here, this entry is -35 plus 35, which is 0. Then I get 6 minus 6 is 0. And finally, I get 15 minus 14, which is 1. So technically, by the definition, I should also show that A inverse is the identity. But next time, we will show that if you have a square matrix and you multiply on one side by a matrix and you get the identity, then that matrix is A inverse. So you don't have to check on the other side. And inverses are unique, and you can read that. There's a proof right there. You can read through that on your own. I'm just going to star this theorem here, theorem 5. If A is invertible, then the equation AX equals B is consistent for each B, and here's the unique solution. Okay, now, and there's a corollary that says if A is invertible, the columns of A are linearly independent. Don't worry too much about all these theorems that we're going to see today, because there's a bunch of them. Theorem 5 is important, and then we'll have theorem 7 towards the end. Next time, we're going to collect all the important facts and put them into one huge theorem. So don't worry yet about what you have to know. One thing you do have to know is how to find the inverse of any matrix, and this is a formula for the inverse of a 2 by 2. All right, so if you have a 2 by 2 matrix and the determinant is not 0, and the determinant is this number here, AD minus BC, If that's not zero, then you have an invertible matrix. And here's the formula. You take 1 over the determinant, and then you swap the diagonal entries, the main diagonal entries, and you make the non-diagonal and main diagonal entries negative. And here's a mnemonic device. Dancing naked bears never cause accidents. Dancing, that's D. NB is for minus B. Never cause, that's minus C. Accidents is A. So it's a silly mnemonic device, but it works. All right, so let's find A inverse for this matrix here. Okay, so we take 1 over the determinant, and the determinant is 14 minus 15, which is negative 1. And then we swap the negative 7 and the negative 2. And then we make the non-diagonal entries negative. And then we clean it up. 2, 3, 5, 7. No surprise there, because I don't know if you remember up here, 2, 3, 5, 7 was the matrix we multiplied this matrix A by to get the identity. And so this really was A inverse. I knew ahead that was A inverse. Okay, part B is solve this system AX equals B using theorem 5. So by theorem 5, remember, I'll just scroll back here. Theorem 5 says the solution to AX equals B is X equals A inverse B. Now this system isn't random. This system is in the form, I wrote it in matrix form, AX equals B. This is our A from above. So we already found A inverse. So by theorem 5, X will be A inverse B, which is 2, 3, 5, 7, 2, 1. And that is 4 plus 3 is 7. And then 10 plus 7 is 17. So there's the solution. That's not actually how you want to solve systems in real life, because finding an inverse is really a pain in the fanny. For a 2x2, it's okay, but it would have been much quicker. You know, if you're stranded on a desert island, you're not going to find A inverse and then just do what I did. What you're going to do is you're going to reduce the augmented matrix like we've been doing since day 1. 5, -2, 1, ... And you're going to reduce that to solve for x1 and x2. So these lecture notes are a little different. Instead of putting the practice at the end, I built them in. So you're going to pause the video now and find the inverse of this matrix. The solution's at the end, so you can check your answer, but you need to do that one. Okay, properties of inverse. These are fun. The inverse of A inverse is A inverse is A. All right. The inverse of a product is the product of the inverse with the order reversed, just like transpose. How does transpose relate to inverse? Well, it's right here. A transpose inverse is equal to A inverse transpose. You can swap the T and the -1. And here, if R is not 0, then R A inverse is 1 over R times A inverse. And there's no property for the sum of the inverse of a sum. In fact, if A is invertible and B is invertible, A plus B might not even be invertible. So this wouldn't even make sense. For example, 1, 0, 0, 1, that's invertible. That's the identity. Its inverse is itself. So if I'm going to add that to -1, 0, 0, -1, that matrix is also invertible. If I add them, I get 0, 0, 0, 0. That's not an invertible matrix. Its determinant is 0. There's no matrix I can multiply that by to get the identity. So So that's why there's no property for A plus B. So let's take these properties and go through them and compare them to the transpose properties that we learned and see if there are similar properties. I think it's easier to remember if you remember both sets of properties. So A inverse is A. Is there a comparable property for transpose? Yes, there is. If you take the transpose of the transpose, you get A back again. All right. The product of the inverse is the inverse of the products in reverse order. We had the same property for transpose. AB transpose was B transpose, A transpose. And these both generalize to any number of matrices. Well, this already involves transpose. So this property, I'll just write same. And for this one, we had a different property. This was RA transpose was RA transpose. I don't know if you remember, but I said if you take a matrix, multiply by 2, and then transpose it, that's the same as transposing it and then multiplying all the entries by 2. There's no property for the sum of two matrices and then taking the inverse, but there is a property for the transpose of a sum. And that was just A transpose plus B transpose. Okay, just want to look at this property a little more carefully with a really easy example. I'm going to let A be the identity. So the inverse of A is the identity, and the transpose of A is also the identity. So A inverse, and A transpose are all the identity. Let's look at 2A transpose. So if I take 2A, twice the identity, 2, 0, 0, 2, and I transpose it, I get 2, 0, 0, 2. That's twice the identity. That's twice A. Okay, let's look at twice A, the inverse. 2, 0, 0, 2. Now, I know what it is by this property, but let's find it using our dancing naked bears and see if we get the same thing. So I want 1 over the determinant. The determinant is 4 minus 0, which is 4. And then we swap the 2's, but we can't tell because they're both 2. And we make both zeros negative, but negative 0 is still 0. So that's a half, 0, 0, a half. Well, sure enough, that's 1/2 A. If I pull out the 1/2, I get 1/2 the identity. Okay, so that property is different for transpose and for inverse. So just keep that in mind. The rest are the same. Okay, so what do you do if you want to find the inverse of a 3 by 3, a 4 by 4, and you don't have a computer? Because you really want to do this with a computer, but I will not make you do anything bigger than a 3 by 3. Here's the algorithm. You augment A with the identity, and you reduce until you get the identity on the left, and what results will be A inverse on the right. And the reason you can do that is the elementary row operations that reduce A to I are the same operations that will reduce I to A inverse. I'm not going to prove that. The proof requires elementary matrices, which we will talk about because they're important. But the algorithm's pretty simple. It's just not that easy to do because this is a very big matrix when you augment A with I. Okay, so let's do an example. Oh, and by the way, if you can't do this, if at some point you get all zeros, a row of all zeros on the left, then A is not invertible. If you can't end up with the identity here, A is not invertible. Okay, so here's my matrix A. I want to find the inverse. So what I've done, I've started us out. I've augmented with the identity, the 3 by 3 identity. And the only hard part is just remembering to go all the way across the rows when you do the row operations. So I'm going to leave the first row alone. Now I'm going to replace the second row with 3 times the first row plus the second row to kill that negative 3. So that's 0, 0, 1. But now I'm going to get a 3 here, a 1, and a 0. And I'll leave the last row alone. Okay. And now what I'm going to do, I'm almost there. I picked a pretty easy one. I've got, I'm almost at the identity. What I need to do is swap rows 2 and 3. So I'll leave row 1 alone. 1, 0, 0, 1, 0, 0. And then I'm going to get 0, 0, 1, 0, 0, 0, 1. And then 0, 0, 1, 3, 1, 0. So now I've got the identity on the left, so I know that A inverse is what's right here. It's a 3 by 3 that's left. 0, 0, 0, 0, 1, 3, 1, 0. All right, so you should pause the video and go ahead and apply that algorithm to this matrix and find the inverse. I put the answer at the end, but I didn't do the computation, so that's on you. All right, we're back again. Hopefully that didn't take you too long. Elementary matrices. An elementary matrix is a matrix that results when you do one row operation to the identity. One, only one. So here are a few examples. This guy is elementary because what I did is I took the identity and I took twice row 2. That's one row operation. This guy is elementary because I swapped on the identity. I swapped row 2 and row 3. And this last one is elementary because I replaced row 3 with 3 row 1 plus row 3. So there's an example of each of the 3 row operations: replacement, swapping, and scaling. All right, let's look at these other matrices and decide if they're elementary or not. So the first one is, yes, elementary, because I took the identity and I replaced row 3 with -3 row 1 plus row 3. The next guy is not, because 2 row operations had to happen on the identity. First, you had to swap rows 1 and 2, then you scaled row 2 by 2. Or scale and then swap. It doesn't matter the order, but that takes 2 row operations to get to that guy, so that's no. This one's a no-brainer because it's not square. If it's not square, it's not elementary because you have to start with the identity. This guy, yes, this is a swap of row 1 and row 3. And this guy, I was about to say yes, but now I'm going to say no because this is a swap of row 1, so row 2 and row 3. And it's also scaling row 3 by 4. So that's 2 row operations. That's not allowed. Okay, why do we care? Here's why. Elementary matrices are so cool. So imagine you're talking to your computer and you want your computer to take a matrix. Here's our matrix A. I don't know why this mouse is so weird. Take a matrix and multiply row 2 by 2. So how are you going to tell the computer to do that? What are you going to do? You can't say to the computer, oh, please multiply row 2 by 2. But what you can do is simply multiply A by this elementary matrix. You take the elementary matrix, it results by multiplying row 2 by 2. And if you multiply that by A, what it does is it scales row 2 of A by 2. All right. If you multiply A by a swapping elementary matrix, so here, this is the swapping one, we swapped rows 2 and 3, it's going to swap row 2 and 3 of A. And finally, the row replacement one, if you want to replace row 3 of A with 3 row 1 plus row 3, you multiply by the corresponding elementary matrix. So it's really amazing. So, here's a practice one for you, answers at the end, but think about what elementary matrix, E, so you're going to have a 3 by 3, what would you multiply A by to get this matrix here? All right. Elementary matrices are invertible because you can reverse what you did to them. For example, if you scale row 2 by 2, how would you undo that? You'd scale row 2 by a half. So there's the inverse of that matrix. You could also find the inverse by using the algorithm above, but that would be exhausting. Well, no, actually for this one, it would be really easy and quick. You'd get that right away. But you can just use logic. So how would you undo swapping? Well, you'd reswap. If you swap rows 2 and 3, if you swap them again, you'll end up with the identity. So this one, the inverse, is actually itself. You don't do anything. Okay, and then finally, how would you undo multiplying row 1 by 3 and adding it to row 3? You'd subtract 3 times row 1 from row 3. So it's hard to say 1, 0, 0, 0, 1, 0, and then there's going to be a negative 3 here, 0, 1. Okay, theorem 7. Again, we're going to collect these theorems in the next section, but an n by n matrix is invertible if and only if it's row equivalent to the identity. So we're going to end with some true-false problems, and we're going to do these together. You might want to pause it and just see if you can do them on your own. Okay, number 1. If A, B, C, and D are invertible, then the inverse of the product is this. That's false because you have to reverse the order. You have to go D inverse, C inverse, B inverse, A inverse. Okay, if A is A, B, C, D, and AD equals BC, A is not invertible. That's true because the determinant would be 0. It's just to say AD equals BC isn't. Another way of saying that is AD minus BC is 0. And that was a condition in that box in the beginning. That was the condition for which A was not invertible. Let me find it. There we go. If AD minus BC is 0, then A is not invertible. And later on, we'll find the determinants of larger matrices 3 by 3, and we'll see that that property extends. If the determinant is 0, the matrix is not invertible. If A can be row reduced to I, then A must be invertible. That's true. It's theorem 7. If A is invertible, the elementary row operations that reduce A to I will also reduce A inverse to I. That's false. It should be I to A inverse. That's the algorithm. That's this statement in red right here. Okay. If A is n by n and invertible, then AX equals B is consistent for each B. That's true. That's theorem 5. If A is invertible, then the inverse of A inverse is A itself. That's a mouthful, but it's true. What's that saying? This is a property. A inverse is A. Each elementary matrix is invertible? Yes. Okay, and that's the end of this section. Next time we'll combine all these theorems together into one giant theorem called the invertible matrix theorem.